Good morning, everyone. Thank you very much for attending this webinar. The webinar is titled "What to Expect when Measuring NSZD Depletion Rates." I also added kind of a secondary subtitle, non-official subtitle, which is a critical discussion about the measurement error in NSZD rates. This webinar is based on a webinar, on a presentation that I gave recently and at the National Tanks Conference a few months ago, and I titled that one "Lessons Learned After 1.5 Decades of NSZD." This invitation was sent to all of the attendees to the National Tanks Conference. So if you're expecting to see that webinar and the title looks different, that is the reason, but I'm going to cover a lot of the materials that I presented at the National Tanks Conference. And this is a bit of a preamble to the talk, and this slide says goes over a common notion in our field, and the notion is that measured NSZD rates are highly variable. And this started with the first guidance document on NSZD rate measurements. That was the API, the American Petroleum Institute guidance document from 2017. And this, I'm quoting this, NSZD rates were an order of magnitude estimates. So right from the beginning, the expectation was that there would be high variability. And the second bullet says is a study that I did that was published in 2022, in which I compared one of the corrections applied to NSZD measurements using site-wide values compared to location-specific values. And there was a big discrepancy between both approaches, and the argument was that that could result in large measurement errors. There's another quote from a paper by Poonam Kulkarni with GSI and co-workers, and she compared different groups of data obtained using different measurement methods, and she couldn't identify a clear bias by any of the particular measurements. Recently, there was a review by the group in Australia, and they indicated that different NSZD measurement options sometimes provide inconsistent results. And recently, I had a paper published at the Lost Line in which I did a summary of data obtained with the carbon dioxide traps, and I basically tracked how the measurement results were changing with different implementations of the traps. And one of the conclusions was that the magnitude of the measured NSZD rates can change depending on critical implementation details. And, just to give you a little more on that, as we became smarter about how to implement these CO2 traps, the NSZD rate measurements became about an order of magnitude smaller than what they were initially. So this is the outline of today's talk. I will describe a very simple NSZD conceptual site model, and also I will describe about, based on what we know about these microbial processes, what is a reasonable expectations of how NSZD rate will vary. Then I will cover some NSZD measurements. I'll talk very briefly about NSZD measurement methods, and I will delve a little more into measurement error concepts, some concepts that are important to understand accuracy for measurements. I will be talking about characteristic scale, noise versus signal, and a concept that has been called signal threading, which was described in a recent paper. And the idea is that the signal that you're trying to measure gets distorted by transport processes and causes some variability. So your near constant signal from NSZD will become a little blurrier throughout different transfer processes. I'll provide an example. I had two examples, but I thought that it was too ambitious. I don't think that I would be able to cover them both. I think I'll be happy if I can cover one of the two examples in detail. And then I'll be wrapping this up and hopefully leave some room for questions at the end. So you can, if you are having some questions, you are happy to, you are welcome to submit them throughout the presentation, and I will answer them at the end. So this is the simple concept, perhaps the simplest concept about NSZD. And I'll go quickly through this because when I looked at the attendees list, I saw that a lot of people have previous experience with NSZD. By the way, I want to thank people from registering. I'm getting a fair amount of people from regulators, industry, consultants. We have people from different parts of the world. We have people from Australia, Canada, and the US. In the US, this week is a holiday week. But we still had pretty good attendance. So thank you for making time for this webinar. So the simplest NSZD concept is that when you have contamination, the contamination spreads through the soil. It sinks in the unsaturated zone, and when it finds a water table, the buoyancy starts making it spread laterally. And then it interacts with both the groundwater, where it causes groundwater contamination, and also with the vadose zone. So this is a course that I took a long time ago, maybe getting close to 18 years ago or so at a site. And the course shows these bubbles, also shows the soil is colored black. And these bubbles actually are biogas. And the biogas is made out of carbon dioxide and methane. And so the idea is that the NAPL is reactive, and the idea is how do you measure how fast it's reacting? Here I indicated that there is biogas being produced, that is methane, CO2. The methane and CO2 are gases. It move away from the source, which is towards the surface. And when they find the ambient CO2, the methane becomes CO2, and in the end, every mole of carbon that is in the NAPL that becomes biogas can be shows up at the surface. Of course, there is interfering mechanisms. All soils produce CO2, and the key question is how to differentiate between one and the other. The source typically is methanogenic, and that is kind of the simplest and most common situation that I have seen at sites. And you can prove that by measuring the methane in the gas phase and the CO2. Of course, microbes are known to use other electron acceptors. If they're available, they would be carried by groundwater, sometimes by infiltration from the surface. And they use them in a sequence. If there's oxygen, they will use it to degrade the contaminants, but they will be sequencing through, as they run out of oxygen, they will shift to nitrate, then metal oxides and sulfate. And then when they run out of everything, they revert to methanogenesis. So at the source, methanogenesis is the main driver, and it's mostly because the microbes have run out of these other external electron acceptors. However, you can measure these different halos of different geochemistries at sites and often find this sequence. So the reactions for NSZD are the following. You have a generic contaminant. In this case, is represented by C8. And in methanogenesis, it produces stoichiometric amounts of biogas, methane, and CO2. And this second reaction occurs at the aerobic anaerobic interface in the presence of ambient oxygen. And there, the methane becomes CO2, and it releases heat. This first reaction also has a heat associated with it, but it's very minor compared to this one. So most of the heat of this reaction is really released when the methane becomes CO2. So I look at this like the first reaction is transforming one fuel into a different fuel, which is methane. And that second fuel burns at anaerobic interface in the presence of oxygen. And if you add up both of these reactions, you get this overall NSZD reaction. And really, this is the basis for the measurements. Really, the methods to measure NSZD rates belong to one of two approaches. It's either a mass balance or a heat balance based on these two approaches. So you can measure the rate of production of CO2, you can measure the rate of production of heat, or you can measure the rate of depletion of the contaminant by looking at how the contaminant composition changes. So what are the NSZD rate measurements? So there's a bunch of guidance documents. As I mentioned, it started in 2017 with the API guidance document. I was one of the contributors to that document. Then all of that rolled into the ITRC updates on NAPL, including a chapter on NSZD. Then an Australian organization, CRC-CARE, put together a guidance document, a technical report, in fact, a series of them, one with different techniques, and then other with case studies. The UK came up with its own different version. There's NAFVAC has a recent fact sheet. The Federal Roundtable Technologies for Remediation has a document here, and recently there's a document released by ASTM. And these guidance documents go over the different methodologies and some kind of the intrinsic limitations of multiple methods, kind of the obvious ones that are expected, but the direct comparison of among different methods are scarce. So the ITRC, the previous document back from 2009, has this approach in which you draw your control volume around including your contaminated source, and you basically track things flowing in and out of that control volume. And people have been focused on groundwater for a long time, but in this study from Paul Johnson and Paul Lundegaard, published in 2006, he focused on the gas species. And what he found is that you would track higher degradation rates through gas fluxes than groundwater fluxes. And the reason is that the main products of NSZD were gases, and they travel through the gas phase. They don't really want to stay in the dissolved phase. And at that point, they discovered that the bulk of the mass really was moving through the vertical gas boundary rather than the groundwater. And that really is what really set NSZD off, and people started looking for different ways of measuring this. The Paul Lundegaard and Paul Johnson tracked the rates by measuring gas concentration through the vadose and feeding that to fixed low diffusion. But Uli Meyer at the University of British Columbia and Natasha Sihora started using the dynamic flux chamber, which is a closed chamber that it gets deployed over the soil. And you start with ambient concentrations of CO2, but if it's getting a flux, those concentrations rise, and then you basically do a mass balance on the chamber. And at the time, I developed this passive CO2 trap, and I thought that the chamber was a good idea, but I knew some of its limitations, and I decided to address those by using passive sampling. And I'm going to have a little more on those in the next few slides. As I said before, you have the key questions to differentiate between the signal that really comes from different, the degradation of petroleum, than the natural signal of the soil that is not related to contamination, such as the production of CO2. So what are the drivers for NSZD? There's three different drivers in my mind. One is L-NAPL composition. So how fast this reaction happens is driven by different things. And the first one is L-NAPL composition. Microbes are known to be selective, so they will degrade some contaminants faster than others, and petroleum is a complex mixture. And the second one is how the distribution of the contaminant in the soil. And the third one is soil temperatures. Microbes are known to respond to an optimal temperature of 40 degrees, but soils are much lower temperature than that. So the microbes start degrading faster as the temperature gets colder. And there's additional drivers that occasionally show up at different sites, including soil moisture, the availability of trace minerals, microbial diversity, and such. Today, I will mostly touch on the first three. So, as I said, petroleum is a complex mixture, and there's a lot of correlations between different properties of the individual compounds and predicted biodegradation rates, including solubility, Henry's law constant, etc. And the idea is that bacteria, when exposed to petroleum, they will be selective. They will choose some things over other. This is a graphic that was published in 2013 by the USGS group, and they basically took different chromatograms for at two different times. This is a sample collected in 83, and this sample collected in 99. And what they saw is that, the other important thing is that there is compounds that I highlighted in color here that are known to be non-biodegradable. So as the bacteria, so these compounds will not be touched by the bacteria, but the others will be. And the resulting chromatogram, the composition looks like this. So these two original markers, biomarkers, have remained constant. The ratio remains basically constant, but the bacteria have degraded some things over others. So this is a heavier hydrocarbon, this is a lighter hydrocarbon, and it's because bacteria have done their selective weathering on it. So this paper came a few years ago, and what they did is they went to a site, they measured the NSZD rates, and based on the initial NSZD rates, they predicted the time when there would be no mass left. And they came back and they measured again. And what they saw that in about this period of 25 years, the rates had dropped between 3 and 5 times. And the degradation rates of gasoline had dropped between 9 and 27 times. So that is proof that the microbes were degrading the easier compounds faster, and as nastier stuff was left behind, then they were chewing on it at a slower rate. So this is a very important paper, and it points out that these rates are not held constant in time. This is one of the other factors that I believe are important, and that is the distribution of the contaminant. This is a sand tank experiment that I did for NAPL distributions. I basically filled up a fish tank with sand, and I changed the water table up and down. And what you will see here is the degradation of the contaminant. So right here, the water table is low, but as the video plays and the water table goes up, you see this redistribution of the contaminant. This is a bit of an ancillary slide. This was for the purpose of visualization of the NAPL distribution. But if you remember that initial state, all of the NAPL was in a single layer, and the microbes would have a hard time getting to it. In this particular state that I'm showing here, the microbes would have easier access, and more of the soil would participate in degradation of the contaminants, and the degradation rate would be higher. If you want to check this more visualization stuff, there's a website, webinar in our website that you can attend for that. The third effect is one of temperature. And this is a simple model that I put together a few years ago. I presented this at the I believe the 2018 or 2016 Battelle conference. If anybody's interested in details of that model, I'll try to describe the model without the equations, which is always an interesting challenge. But the model assumed contaminant distribution, a vertical contaminant distribution. I grabbed that from published data at the Bemidji site. And then I plugged in the temperature, the average temperature. So this is the groundwater temperature on top here. On the bottom here, this jagged diagram are daily temperatures throughout the year. And then using the heat equation, I predicted the soil temperatures at different elevations and the time temperature history at each elevation. This is the overlaid contaminant distribution profile just to illustrate that each elevation goes through different temperatures throughout the year, and those will control how the microbes will work. So I basically corrected biodegradation rates using published biodegradation rates from the literature and how these change with temperature. So I basically was pasting together a bit of a Frankenstein of a site to try to get an idea of how things should vary. So, you know, there's a lot of uncertainties about this model, but the main point is I was trying to understand how degradation rates would vary throughout the year based on ambient temperatures and their effect on the local soil temperatures at different depths. And this is one of the model solutions. So this is throughout 1 year. These are the biodegradation rates that were predicted by the model. So the model offers continuous, nicely behaved, idealized degradation rate throughout the year. And the red line is that one. The discrete points were published data from Natasha Sihora's work using the dynamic closed chamber. So really, there was some general agreement about the order of magnitude of these measurements and how they would vary throughout the year. I already went over, you know, the model assumptions. But the point is that if you just account for ambient temperature, ambient temperature fluctuations, you can expect that these rates would vary throughout the year. This is the variation in the x-axis. The magnitude of these NSZD rates, as I indicated before, would depend on the NAPL vertical distribution and also indirectly on the composition, basically the difference between fresh versus weathered. So this is just to illustrate what a rational expectation of what the NSZD rates would be, how they would vary. The challenge here is that these rates will change as follows. First, they will change throughout the year based on the annual soil temperatures on the site. But then as the contaminant gets weathered, this scale in the x-axis shrinks. And, you know, I'm just borrowing those numbers from the Davis paper. And this would shrink. And really, you have to keep an eye on different time scales. There's an additional time scale that I'm not showing on this scale yet, but I will discuss in the next couple of slides. So I described how these NSZD processes happen and how they're expected to vary throughout the year. And now I'm going to go into different measurement methods. This is the heat balance approach. I'm not going to go too much into that because mostly I want to use the approach of the CO2. However, there are applications of what I'm going to be discussing to the thermal gradient. And those are based on basically the time scale that the measurement has to be conducted at. So the people from Australia looked at that method and had a hard time reconciling that method with other methods. And I have some insight into why it might be happening, but really has to do with the use of these two different time scales for the measurement. I'm not going to be talking much about the gradient method. I'm basically going to skip this slide. And I want to focus on the two other measurement methods, which is the dynamic closed chamber. This is how it looks. You have a CO2 sensor connected to the chamber. The gas is recycled from the chamber to the sensor, and you deploy this over a few minutes, and you get the input from the soil into the chamber, being the flux measured. And this changes quickly throughout the day based on ambient pressures and temperatures. And this is a typical measurement at a non-contaminated site from literature. You even get negative influxes because basically the soil breathes in and out once a day based on ambient pressures and temperatures. The second measurement is the CO2 trap, the passive CO2 trap. And here we capture the CO2 as it leaves the ground using a passive sorbent. And then, as I said, the ambient pressures can change, and that can drive gases into the soil. And to account for that, we have a second layer of sorbent to keep this ambient CO2 away from the measurement, which is in the bottom layer. Additionally, we have two colors of the CO2 depending on its source. We have an all-carbon source coming from the petroleum, and we also have young carbon, which is coming from the natural processes of the soil. This is the difference between these two types of CO2 is done using radiocarbon analysis. So here I want to talk about these basic concepts for measurements in soils. This is coming from a paper from Art Corey. I had the privilege of knowing Art. He died recently at the age of 99. And even at that age, he was one of the smartest people that I have ever met. And he was really a true inspiration. I also consider him a friend. And this plot here shows how measurements of soil properties change based on the sample size. So I'm going to illustrate that with hypothetical concept. Imagine that you're measuring the porosity of gravel and you're using a spoon. You use your spoon and sometimes you get a large cobble of gravel. Sometimes you get nothing. Sometimes you get a little cobble of gravel, and this measurement varies a lot. As you increase the spoon size, you continue to have some variability, but at some point that starts being reduced. So when you use a bucket, then your measurements of soil porosity should stop varying. And the point where that happens is called the book calls it the minimum volume for reference element, or REM, but I call that the characteristic scale. So the bucket captures the characteristic scale of that property much better than the spoon. So this is about variability. The second concept is one that is called the signal shredder. And imagine that you have a signal that is constant at the source, like, you know, for example, the production of methane below the water table. So methane is a gas. It starts creating these little bubbles. The little bubbles grow, and they eventually burst. So this release of gas from the subsurface is episodical. And in addition to that, you get the transport process of the CO2 and methane towards the surface. And you get this, you know, this process is thought to be diffusion driven, but when it gets to the surface, there is this advective element imposed to that bulk flow based on diffusion that basically smears your flow up and down and creates these waves throughout the day that come in a cyclical manner. So this paper from 2015 called that signal shredder effects, and that's also how a compilation of NSZD data referred to this from Sanjay Garg and co-workers. The third concept here is signal, the concept of signal versus noise. I talked about, for example, how the CO2 is produced by the soils. So the CO2 produced by the soil would be your noise. The total CO2 rate would be your total signal. And if you subtract both, the signal from NSZD would be the leftover. Here, there's two different approaches. One is site-wide correction, which is using the background correction. So you go to each one of these locations and measure the total CO2 flux, and you measure the CO2 flux on contaminated location, and this is your background corrected signal, which would be what is attributable to NSZD. There's a second approach. It's not available for all methods. But if you use the radiocarbon correction here, you can basically break down the contribution from all carbon and modern carbon and each one of these corrections. And this might be a little confusing because both of the equations look exactly the same or very similar. However, here and in the left, the noise is assumed to be constant at the entire site. And here on the right, the noise is assumed to be location specific using the radiocarbon. So that's basically what I was doing at a site, at a study. I don't have that study yet here in my slides. So here I am going to the third part of the talk. I want to take a little bit of a moment here and try to do a poll. Let's see if I can run this. Yeah. So I'm gonna launch. I have two poll, and I have two questions here. So I'm gonna launch this. I don't know what it's gonna do. It might show both questions, and if you want to answer both, that is fine. Or yeah, let's do that. If you see both questions, just answer both if you can, please. The first one is methanogenesis is a degradation process that is slower than those driven by external electron acceptors. There's two choices, true or false. We're starting to get some answers. And then the second question is, all NSZD measurement methods provide NSZD rates that are about 1,000 gallons per year. True or false? So thank you for answering this. This is very interesting. I must confess that this is a tool that I've only started using recently, but it's very interesting. So we got a fair amount of answers now. I think that the rate of answering is now low, so I'm assuming that everybody is done with their answers. So the answer to the first one, that the methanogenesis is lower than other processes, most people answered true. There's about 30% that answer false. And I would say that both might be correct. So if you look at flask and you look at how fast the contaminant degrades in that flask, I think that the people that answer true are correct. However, the thing that is missing from that concept is that methanogenesis is more widely distributed because it doesn't depend on external electron acceptors. Most of the source will be methanogenic. And when you compound these rates over a larger area than using external electron acceptors, you probably will get a higher degradation rate. So I would have answered false, but only because I am thinking about the distribution of these processes at a site level. So the second question is, all NSZD measurement methods provide rates about 1,000 gallons per year. Only about 20% answer true, and the majority answer false. And I would say that I've heard this sentence often from the industry, and I believe that that is not true, that the rates of NSZD depend heavily on how you control on the method used and how that method accounts for error. So I'm going to end the poll and move on with the rest of the talk. We're at about 30 minutes into the talk, so I do want to get to the other parts. So initially, we had a compilation of NSZD rates from Sanjay Garg and others, and a previous study from Tom Palaya looked at the remediation efficiency of different remedies. I'm sorry I'm missing the scale here, but these are gallons per acre per year. And this was really why people got excited about NSZD. So on the left is what remedies do. On the right is what NSZD does. And the case here is that a lot of sites, you were getting NSZD rates equivalent or higher than some of the active remedies according to this compilation of data. Recently, this was data presented at one of the Battelle conferences. Somebody did implemented a measurement method, and they reported achieving something like an average site-wide average of 8,000 gallons per acre per year. So obviously, this would be a very high number, and very few remediation methods would be able to touch it. So that caught my eye, and I started looking at the magnitude of the rates, and this is including a recent publication from July this year. And using the CO2 traps, I started tracking the history of these measurements using that data and comparing it to some of the published ranges, the published compilations. So this is what I looked at. I already explained this, so I'm going to move away fast here. There is a site in which they implement, in which they look at different implementations of soil gas flux base measurements for NSZD rates. So on the left, we have here what they call the survey mode of the dynamic closed chamber, but this will give you a short-term measurement. They implemented robot, basically multiple robots that connect to the same CO2 meter. And using these robots, they would get the time series for the soil CO2. And they also implemented the NSZD method of the passive CO2 trap. So this is the data here using the time series of the dynamic closed chamber. They did this for about 20 days. By the way, this data is available at the IPEC website. This was presented in 2015. And to my knowledge, this is the only data series at a contaminated site using the long-term deployment of the chambers and comparing that to the CO2 traps. So here you have the short-term measurements. In the first couple of days, they have this data, but then they got precipitation. The flux is shut down for about 2 days, and then they were reinstated. And then you get this daily pattern and now reinstated. And if you compare that to the traps, you would get the average here on this time series, and the average is within the range of the total CO2 flux from two traps that were neighboring. However, when you apply the radiocarbon correction for the traps, this is the red fraction right here, the numbers are much tighter. They're about within 3%. And really, the conclusion of this report was that the trap data was consistent with the dynamic closed chamber, and that is true, but that is mostly for the total CO2 fluxes. They really didn't report what the calculated value for the NSZD rates would be based on this time series. And really, one has to keep in mind that most of the dynamic closed chamber implementations don't collect this full time series over 20 days, but they collect a single time measurement. And they also, most people don't apply the radiocarbon correction to this. Some people have tried that, but my argument is, why would you do that on a number that is highly variable? So the initial data reported by Kevin McCoy, I participated on that, and that used an early version of the CO2 traps. And this is the ranges. These are the middle 50th percentiles, and you get a number between 1,000 and 3,000 gallons per acre per year. These were background corrected, and they were not radiocarbon corrected. This data set was incorporated into the Sanjay Garg data set and also into the Poonam Kulkarni compilation. And this CO2 traps, this technique changed because we applied three different modifications. The first one was to use only the radiocarbon correction. The second one was to change the connection of the receiver to the soil. Initially, one of the methods that was considered was digging a hole in the ground, putting your receiver pipe and refilling that hole. The API guidance document even has a procedure to recompact this to the initial field compaction rate, but that is very difficult. And we had a project in which we saw the effect of these two that was very large, and we really stopped recommending this one right here on the left, and only recommended what I call the direct push. This is a shallow receiver, only intrudes about 2 inches into the ground. You leave the soil inside the receiver intact, and then you deploy your trap. The third change that we implemented was the actual footprint of the traps. The traps shrank in height, and also we used a rain cover that was a smaller diameter. And this is important if you have wind at the site, because the higher your instrument is here, the more exposed to higher elevations is, and it can cause a bit of a Venturi effect. It's exposed to high velocities here that suck gases from the ground and cause higher rates. So this slide really tells you how these changes were implemented and how the different reports use different versions of the trap, starting from the original data set from Kevin McCoy, what I call the first prototype, and then the second generation and the third generation. So the Garg and others compilations use the McCoy data, and Poonam also used those. But Poonam Kulkarni also used third generation traps, and there's only 2 studies that only use the third generation traps. I already went over that. I reported the effect of the radiocarbon correction, and in this paper from 2022, I had data from multiple sites in which they had reported total CO2 rates and also the radiocarbon corrected rates, and that allowed for calculation of both approaches. And this is how the data looked like. Here we have the perfect agreement between both approaches would be this solid black line. Here is the fossil fuel flux using the radiocarbon correction on the y-axis, and on the x-axis is the background corrected fluxes using the same deployments of the traps. And what you see here is that very few of the data really follow the ideal correction. And in fact, the background correction had some negative numbers here, which don't make any practical sense. But a lot of the measurements were showed actually a higher total flux using the background correction and the radiocarbon correction. And this is really one eye-opener for me, because it told me that the radiocarbon correction was location-specific, and assuming that a single correction was that was site-wide specific was valid, was not a very good assumption. We had discrete individual corrections on each one of the 5 different sites that I collected data from, and really none of them behaved well, with one exception that is somewhere over here. This was a dry site in Australia, in which, in fact, both of the corrections really agreed upon. This is the last effect. This is the receiver implementation, the receiver installation method. Here you have the dig and refill versus the direct push. And we have a site. This is available data publicly. This is at the Colorado the Department of Public Health and Environment. And this site had done multiple sites using the first method. And at some point, they changed to the second method, and the rates dropped by an order of magnitude. So when you look at these three corrections, the data from those three corrections is available at two reports. One is that 22 paper that I mentioned, that I explained, and another one is a study ran by NAFBAC, the Navy people. And they had 5 sites. They reported average at all of those. So these are the compilations that I showed before. First, the Kevin McCoy data in blue. Then we have the Sanjay Garg ranges, the Punam-Kulkarni's ranges, and the 22 study was, this is how the data looks like. So your range has now changed from the initial 1,000 to 3,000 gallons per acre per year. Now it goes from about 200 to about 1,000 gallons per acre per year for the middle 50 percentile. The mean is now about 250 gallons per acre per year. The studies from NAFBAC are even smaller, but the historical compilation that we have for all of our sites is following this one more closely. So why does this reduction in measured NSZD rates is important? I have 3 quick examples here. We have one about remedy transition, which is the populations, one that is using that example from the Battelle conference, and a third one using site longevity. So this is the compilation that I gave about the remediation. The remedies, what the removal rates are for different rates. This is the Sanjay Garg data, and this is the powerful message that NSZD exceeds most remedies at many sites. The compilation that I presented from 2022, it's a smaller value, about an order of magnitude. And the importance is that now the fraction of NSZD, the fraction of sites where NSZD exceeds active remedies is smaller. It still happens, but this is smaller. And this is the NAFBAC data. So the bottom line, NSZD can outperform active remedies, but not as often as we initially thought. This is the second hypothetical example. This is from the ASTM. This is a case in which they assume 32,000 gallons per acre. And if you have 700 gallons per acre per year of NSZD losses, you have 30 years to nearly complete depletion. If you change the NSZD rate from 700 to 150, which I believe is more realistic, you have about 130 years to nearly complete depletion. Now, this doesn't even account for the fact that the NSZD rates are going to vary with composition. So, considering what your average is will change your expected site longevity from decades to perhaps centuries. And perhaps the final remedy that the NSZD is it's acceptable would not change, but it seems that these comparisons should be based on best available technologies and best available data. The best available data obtained with best available technologies. The third quick example here, I want to wrap this up so you guys still have a chance of ask some questions. I think this is a summary of why it's hard to interpret NSZD rate. And the reason is why you need to keep an eye on 3 different time scales. What are these 3 different time scales? One is the short term. And the variability of this signal is often one in which you have, it varies daily. And really, I didn't mention this, but when I presented this data, I calculate the average up to that point. And this is this red line. So this red line tells you that the characteristic scale of CO2 fluxes is about 5 days. And then you have the seasonal variability. I presented this model predicted expected changes in NSZD rates, and then you also have to keep an eye on long term. So the characteristic scale depends a lot into what situation you're looking at. You know, if you just want what your NSZD rate is right now, you might want to measure for at least 5 days. But this process changes seasonally. So in a way, the characteristic scale is a year. If you want to account for seasonal temperature variations at your site. But also these rates will change over the long time. And that changes over decades. So this is really something that made me think of why people are having a tough time interpreting things. These errors stack. If you don't start with an initial short-term measurement, then your long-term measurement is going to get blurrier, and even your multi-decade measurement is even going to be difficult to interpret. I'm close to the end. This is a table in which I talk about, how different methods handle the characteristic scale and the noise in different ways. You have the superficial CO2 flux, you have the dynamics closed chamber, and the CO2 passive trap. I didn't talk much about thermal flux, but there's two approaches. People started using these background corrected temperature profiles in the soil. And then I did something that now people are calling the single stick method, which basically says that you have to conduct the heat balance over the long term because you have ambient temperature fluctuations that single time measurements are going to miss the characteristic scale. So this table tells you how this handled them. The dynamics closed chamber is mostly used as a single time measurement using the background correction. The automated system was used in that study that I presented, but they didn't mention how they corrected for noise. I would love to see the background location behavior there. The passive traps measure over multiple days and use the radiocarbon correction. And that is really the entire description of this. This is some criticism that I had on this data that was presented at the Battelle conference. They used the single stick method, and they presented a range of values, but they use different locations, but they use soil transport properties from reported values. And I think that is a huge shortcoming in any site because these ranges are very high. And they also reported seasonal results that were not consistent with the conceptual site model. They reported the highest rates that they measured were at the beginning of the year when it's cold. You know, why were the microbes chewing on the petroleum faster in January than in October? I don't know why that is. The number that they came up with was 8,000 gallons per acre per year that led to site closure. And I don't know, that really made me a little uncomfortable. I'm glad that I wasn't the person presenting that. That was the data that they presented, but I already described how that was obtained. And really, this is a quick checklist that might be helpful. It provides some flags. If you see these flags, you might want to think a little harder about your site and whether or not the data is making sense. So that's all I have. If anybody has any questions, I'll be happy to answer them. I already have a few here. I think your stoichiometric equation is missing oxygen on the left side. Thank you very much for pointing that out. I am pretty sure, I won't question that. I'm pretty sure that's something that I would certainly see myself doing. Thank you for pointing that out. There's another one. Does the heat generated by the methane degradation offset the seasonal temperature fluctuations? I wouldn't say offset. Offset is if it's much bigger than those, and that is not the case. The study that I did using that model, and I'll be happy to share this with you. Whoever answered that question, please contact me, and I'll be happy to talk to you about the thermal gradient method. There's some equations there, I need to warn you, but that was really eye-opener. And the fact that people are actually preferring the single stick method for thermal measurements, I think that that is telling me that people struggle with the background correction all the time. I know why that is, because the locations are not the same. The assumption of background correction is that the contaminated, the uncontaminated locations are identical except for the contaminant. And this identical assumption is very rarely met at a site. You have different vegetation at a site, you have different surface temperatures, you have different lithology profiles, and you might even have different groundwater temperatures. So the background correction doesn't work, but the long-term does. So I'm not sure I answered your question, but the measurement really accounts for both. But if you do the long-term heat balance, you basically end up with same heat stored in the ground that you started with. And that the implication of that is the heat that comes from the ambient is the same that comes out over a 1-year term. How reliable is the measurement of degradation due to active remedies? I don't know. That's a site by Tom Palaya. It's available on the internet. You should look at it. It might be. My impression is that that is high quality data. I don't think that there were. That is just my impression. How much does the flux change across the site? What density of measurement points is needed for our accurate calculating total degradation amount? That is an excellent question. Thank you very much for answering that. The spatial bias, the calculation of NSZD rate goes from point measurements to aerial measurements over the extent of the contamination. And very often I see people going to the site, trying to find where NSZD rate is expressing itself at the highest rate, and they do the measurements at those locations. And there is a chance that there is a measurement bias by sampling. You're sampling where you know NSZD rate is the highest. A better approach, and is one that I recommend, is take your entire footprint of the contamination and then break it down into high, medium, and low spots. And then allocate the same number of measurements to each one of those types of locations. And then you might get something that is more representative. Yeah, thank you for that calculation. I don't have any more questions. If anybody has one, please submit it, and I will try to answer it. So there's one more here. It says your description of signal shredding and characteristic scale are very similar. Are these two things the same? And that's an interesting question. And I had to think about that a little bit. You know, signal shredding is how your signal goes from an expected constant to something that varies. And this is caused by you know, the nature of the transport processes that is related to that particular signal. And that can be heat transport or gas transport. So it's how the signal actually varies. The characteristic scale is the solution to that variability. You need to measure over a certain time or over a certain area. You know, the previous question in which people say, what is the characteristic scale for the surface? That is a critical one. And I think that I have seen very few discussions about that. Yeah, so characteristic scale is how we need to account for that variability produced by signal shredding by the measurement method. I think that is all I have. We're getting to the time limit. We still have a lot of people of the attendees here in the audience still listening. Thank you very much for sticking to the end of this presentation. I very much appreciate it. For those in the US, I wish you a very happy Thanksgiving, a good time with your family. And thank you very much for all of you for attending. Thank you very much.